Our next topic deals with linear functions and applications of those. So to begin with, let's think about our definition for a linear function. So any relationship which we can designate as f of x or g of x or h of x or whatever is just a definition of an equation where instead of writing y equals and then some slope times your predictor variable x plus b for your y-intercept, we can replace that with a function of the input variable such as f of x or g of t or h of q, whatever the letters are. But these are going to be real numbers for m and b, and that creates a line. Now in this case, f depends on the value of x as we have it written. You can think of y and f of x as like synonyms in English. They're sort of interchangeable, but it says if you put x in, this is what's going to come out. And you can denote that as either y or f of x. Now let's consider a simple example. So let's say that in a chemical reaction, the amount of product, what you get out of a reaction, which we'll denote as P, depends on the amount of one of the reagents or chemicals that you put into the reaction. So we're going to let P be defined as the function of C. So f of C equals 4.2 times C. So P is the amount of product, which we'll measure in grams, and C is the amount of the chemical or the reagent in grams used in the process. So it's what you put in to the reaction. Now this is going to be a linear equation which passes through your origin. So if you think about it, if you don't put any of the reagent in, you shouldn't get any product out. So that sort of makes sense that it's tied down at the origin. Now what types of questions can we ask in this type of scenario? Well, one thing we could do is say, how much product, P, would be produced if 3.5 grams of the chemical is used in the reaction? So in this case, we go back to our equation, which was, remember, f of C is 4.2 times C. So we plug in the amount of chemical we put in, 3.5 grams, multiply that out, and you get 14.7. So if 3.5 grams of the reagent is used in the chemical reaction, then the yield, or the amount of product we have, would be about 14.7 grams in this case. Now another question we can ask is if I want to produce 6.3 grams of the product. So if I want the final answer or the P amount to be 6.3 grams, how much of the reagent do I need to put into the chemical reaction? So in this case, we have to solve the equation 6.3 equals 4.2 times C. So we divide both sides by 4.2 and we get that C needs to be 1.5. So to yield 6.3 grams of the product, the reaction needs to have 1.5 grams of the reagent put into the chemical reaction. Now let's consider another example. In this case, we're going to look at two concepts that are sort of tied together. We're going to look at supply and demand. Now, a lot of times these can be represented by linear functions. They're related to price, and we can find linear equations relating supply and price and also relating demand and price. And then we can plot these on the same sort of coordinate system and then look at times when there may be surplus or a shortage and so on. Now typically more supply implies lower price and higher demand implies higher price and all this stuff. But you want to be careful because price ends up being plotted on the y-axis, so you have to be careful with how you read the graphs. So don't get tripped up by the notation. So in this case, let's suppose that a regional store manager is looking at the price of mangoes And he relates that to the quantity demanded using the function P. Price is the demand based on the quantity equals 1.6 minus 1/10, or 0.1 times Q. So P is the price per mango in dollars, and Q is the quantity demanded in thousands of mangoes. Also, the supply and price are related by this second equation, where the price is a function S of Q, S just for supply, and it's 0.5 Q, or 1/2 of Q. And again, price is denoted as P and is the price per mango in dollars, and Q is the quantity supplied in thousands of mangoes. Now we can make a graph of this, and what your CDF player shows is that the demand curve is in sort of that pink line, and the supply curve is the blue line. So you can see that all we've done is graphed these on this coordinate axis system. Notice price is on the vertical axis, and then the amount supplied or the amount demanded is on the horizontal axis. So what types of questions can be asked? Well, first, we could be asked to find the quantity demanded, okay, if we know the price is set at $1.20 per mango. So if we could go up to the axis and draw a line across from the $1.20 mark and then go down, okay, to the supply and demand axis, we could figure out where that 120 intersects, okay, that line, go down vertically and get these amount demanded. Now the way we do this algebraically is simply to put the price that is set, the $1.20 in per mango, equals 1.6 minus 1/10 of how much is demanded, the quantity Q. So we solve this, so subtract 1.6 from both sides, so you get -4/10 equals -1/10 of Q, so then divide through by the -1/10 to get 4 for the value of Q. Now keep in mind, Q is in thousands. So when the price is set at $1.20 per mango, then 4,000 mangoes will be demanded. Now we can also work with the supply line. So let's say that we want to know the quantity supplied when the price is 90 cents per mango. So again, if we could go over to 90 cents on the vertical axis, move that over this time to the supply line, which is the blue line, and go down to where that intersects the horizontal axis, that would tell us what the amount supplied would be at a price of 90 cents per mango. To solve algebraically, we just set the price of 90 cents equals the linear function, 1/2 of Q. So then divide through by 1/2 on both sides, and you get that Q is 1.40. Again, this is in thousands. So when the price is 90 cents per mango, then 1,400 mangoes will be supplied. Finally, the equilibrium price is where the demand line and the supply line intersect. So it's going to be this point right where the pink and the blue line intersect each other. Now we can find that by setting the two equations equal to each other. So 1.6 minus 0.1 Q equals 1/2 of Q at what value for Q? So we solved that for Q, so add 1/10 Q to both sides. So you get 1.6 equals 6/10 Q. So then Q is just 1.6 divided by 0.6, or 2 2/3. Now if we round that off to whole numbers, that would be about 2,667 mangoes. Now to find the actual price instead of the quantity, we could use either equation. We could plug the 2,667 mangoes into the equation, but keep in mind Q is in thousands, so we really need to plug in the 2 2/3 value. I'm going to use the 1/2 Q equation because it's less arithmetic. So basically 1/2 of 2 2/3 is 1 1/3. Or if we were, again, rounding this off, we could say that is about $1.33 per mango. So the equilibrium price is $1.33 per mango.